Who are we missing?
A lot of people.
1, 2, 3, 4, 5, 6, 7, 8. Does seem like we're missing a couple people.
What's her name?
Heather.
And what's her name?
And Kirsten. Yeah, okay. What?
What's her name?
What's her name and what's her name?
No, I knew that was here. She wasn't here for musicology.
No, for some reason it
Doesn't that look like it's the wrong screen resolution?
Yeah.
Drives me crazy. Let me fix that.
He wants to turn off the cable.
No.
Part of the outtake.
What resolution you think today?
Oh, you guys, yeah.
I'm gonna guess that. That's too big, huh? Let's try it. Does that still look bad?
It's off center. It's going to bother me.
It's bothering me. Oh well.
You shouldn't even have pictures there.
But she doesn't know how to read those graphs, and I bet you don't either, or maybe you do. But your book does a terrible job at covering them. Huh?
This is mine.
Okay. So we're going to talk about quality control in the clinical chemistry laboratory. What's the purpose of quality control?
So you monitor to check everything in order?
Yeah, you want to monitor, make sure your equipment and your lab is running properly so you get, you know, the proper values for patients' samples, right? So ISO came up with these 10 quality ensuring items. One thing is, the first one, having an effective quality system, right? What are quality systems, you know? So quality systems typically, I think, fall under the categories like good clinical practices, good laboratory practices, and good, you know, what are those other manufacturing practices? So you want to make sure all your equipment, you have to have good maintenance and everything on those, right? Ensuring valid and timely measurements. So when you do the periodic checks, that they're valid and periodic, right? Using calibrated measuring and testing equipment. You know, if you're testing equipment, that stuff has to be calibrated, right? And measuring. Appropriate statistical techniques. If you don't use the appropriate statistical techniques, you're going to come to invalid conclusions, right? Developing a product identification and traceability system. So, what does that mean?
Like the numbers on the pipettes and the lab.
Yeah, like the numbers on the pipettes, or for materials, the lot number, so you can trace it back to, you know, the materials that you use. So if there is an issue, you can say, oh, it was because of this material, we got to throw everything out that was made with it, right? Maintaining adequate record-keeping systems, and again, that goes to the traceability, right? Ensuring adequate product handling, storage, packaging, and delivery systems, right? Oh, these are all boring type things, right? Maintaining adequate inspection and testing systems, that kind of goes along with, I mean, a lot of these seem kind of redundant, don't they? Maybe that's why everybody hates this book. Establishing processes for dealing with non-conforming items. So that's one of the things you have to do for quality control. When you get something that falls out of sync, you got to figure out, you got to have processes to deal with that. Because when your quality control values are off, you got to know if you need to throw away the run, or if you can keep doing it, or troubleshoot what happened with that. Ensuring adequate personnel training and experience. Oh, you didn't know we were in this room.
Sorry.
That's all you guys do.
So, primary analytical goals of a quality control program. First and foremost, you want to establish and maintain accurate and precise methods for your lab. Determine the level of precision needed by the lab and maintaining that level of reproducibility. So you need to be able to know how precise you have to be and then be able to maintain that, right? And that's quality control goes to make sure your preciseness is being maintained. I'm bad at words. Ensuring that analytical systems are stable and operating according to established performance specifications. Ensuring regulatory requirements related to CLIA compliance are followed. Who knows what CLIA is?
Clinical laboratory, something.
What is, I forget, but who's taking the business class? Or the management class? So you should know what CLIA is.
I should.
I don't know what I think it's something like.
CLIA 88.
But I know it is.
I think it's Clinical Laboratory Improvement Act of 1988.
Yeah.
Amendments?
Laboratory improvement amendments.
I remember 1988.
Yeah. So you got to make sure you're following the law, basically. Providing objective analytical benchmarks for methods and instruments so that continuous improvements of existing methods are achievable. And then to achieve those goals, you want to meet the top 10 quality assuring goals, institute policies that govern patient preparation, because if you remember, pre-analytical variables, you know, are one of the major errors in the lab, right? It's not the analytical phase, the majority of them is pre-analytical, right? Which is reducing pre-analytical variables, errors. Maximize the effective use of the laboratory's resources, personnel, equipment, supplies, and physical facilities. So what are the goals? What do you think your first goal should be? You're going to read it.
I was going to read it down, I don't want to make you sad.
I looked right at you because I could tell you were about to read it. You need to define how accurate and precise the laboratory should be, right? How accurate. So how do you do that? Do you know what you got to look at? So I think CLIA 88, they come up with the different analytes and the amount of error that's allowed for each one of those analytes. So basically, you use your accuracy for your result and, you know, how accurate your equipment is. What does that tell you, the accuracy? Do you know that word? Yeah, but how far away you're consistently from that target is what? No, standard deviation is the scatter. But how far away your mean is from that is your bias. That's your equipment's bias. So you need to know your equipment's bias, and then your standard deviation, your precision, you add those together, it needs to be below the total allowable error based on that law. So if you're not below that, you need to revamp the system and improve your accuracy or precision, or if not both. Okay. And that goes into how precise and accurate must the laboratory be, right? And then what is the acceptable analytical error based on the use of the test result in clinical care? So there's some acceptable analytical error, and that's what I was telling you about, the total allowable error that CLIA. I think there's a table in your book that tells you all those. Too much control can waste time and materials, right? So if you're controlling too much, it costs money and time. So you know, labs don't like wasting money. Nobody does, right? And does error reduction improve medical diagnosis, treatment, or prognosis? So if you're reducing error to the point where it doesn't have any clinical benefit, there's no point in being that precise or accurate. You only want to be precise and accurate enough to where you're going to see the clinical benefit. If you keep pouring money into it, and you don't get any improvement on the clinical side, you're wasting money, right? You're making the cost for everybody go up. So, places to start for goals: precision and accuracy demanded by CLIA 88. Precision and accuracy attained by most laboratories. Where do you get those? From communications with other labs, proficiency studies. We talked about proficiency studies. Who knows what, other than you, what a proficiency study is? So those are required by labs to maintain their accreditation. They have to do these proficiency studies where you get these outside groups like CAP. Anybody have an idea what CAP stands for? Something American Pathologists. College of American Pathologists. That's one of the people that does these proficiency studies, and that's where they have a set of tests that they send out to all the different labs. So you get, they do these group means and they group standard deviations, and you see how well you are compared to everybody else, where you lie. Precision and accuracy required by the clinical staff. So this is important too. If the staff needs a certain amount of precision and accuracy, that goes to your clinical, outcomes, right? If they need that, they're going to tell you. So even if it's more so than what's demanded by law, you're going to have to come up with that because that's going to have the clinical outcomes. The total allowable error is composed of the individual components. Each component can be a source of imprecision or bias. So remember, imprecision is the standard deviation. Bias is how inaccurate your test is. The more completely one can identify the components of the error, the better one can make adjustments to reduce the error. I'm trying to make this more like Shakespeare. Right? No, that's just a typo. So, the more completely one can identify the components of the error, the better one can make adjustments to reduce the error. So that could be training staff to pipette better, doing more routine maintenance, clean off electrodes on chemistry machines, things like that. So the total error is going to be equal to the sum of all your bias errors plus 1.96 times the standard deviation of that method, right? So an example, requirements for glucose total errors to be less than 6 milligrams per deciliter. You know the imprecision is plus or minus 2 milligrams per deciliter. So how biased can it be after that? Do you know how to do this? Simple math, right? So 6 equals X milligrams per deciliter plus 1.96 times 2 milligrams per deciliter, because this is your standard deviation, right? And then that's going to equal what? About 2 milligrams per deciliter is the maximum amount of bias your equipment can have then. Does that make sense? So total error includes the bias errors and your imprecision errors. So performance required for proficiency testing, CLIA 88 has set allowable error criteria for 154 tests at the target values. So why do they select target values? Do you know? Like if you look at glucose here, the target value plus or minus 6 milligrams per deciliter or plus, I can't see that. We are cut off, aren't we?
10%.
Yeah, or plus or minus 10%. So those are your target values, I guess. So medical decision limits. This is what I was just trying to allude to. What do you think medical decision limits are? So those are the analyte values at which some medical personnel is going to make a decision about a diagnosis, right? So I think fasting blood glucose, if it's above what? I think 110. It labels you as pre-diabetic or diabetic, I forget. Not fasting, the glucose tolerance test, right? right? So that would be like a medical decision limit. So you want to measure your accuracy and precision at these medical decision limits when you're coming up with, you know, how much error you're allowed. So this is where you want to measure it, at the medical decision limits. So the establishment of analytical accuracy and precision performance criteria should be based on these medical usefulness requirements. So you want to minimize the error at these medical decision limits, because if you're off, if you have a lot of bias elsewhere, but it really makes no difference as to what the diagnosis is going to be, it doesn't matter. What matters is when you have a lot of imprecision and inaccuracy right at these medical decision limits, because you can go either way. You want to be as accurate as possible and precise as possible at the medical decision limits, if it's going to affect patients. So this is something they do in the hospitals and stuff. They have these significant change limits. Basically, these are, you know, if you're taking values from patients daily, there's going to be normal variation, daily variation between those. So physicians will make these clinical decisions based on day-to-day differences in patient test values. The actual accuracy and precision of the measurement procedure will directly influence the medical interpretation of the day-to-day changes. So this significant change limits, it's like the limit. If you exceed that significant change limit, it says that change is significant, and there might be something that has changed in the patient, right? Does that make sense? You're taking these day-to-day values, you're going to see a normal variation. I love drawing dots for some reason. Normal variation of those values that should follow some sort of distribution that can be recorded. And the significant change limit is if all of a sudden we got something way out here, maybe there's something that's changed in the patient's, you know, condition that has caused that. Because it's the likelihood at this point looks like it's less than 1% that you randomly get a point way out there, right? So they use this significant change limit to look for something that's changed in the patient's physiology or pathology to make a diagnosis. So it's based on the assumption that the usual standard deviation, which are these dots I drew, your usual standard deviation represents day-to-day method variability. So you're going to just see that with just the normal method. Standard deviation of the difference between the two separate analysis of the same sample on 2 different days is related also to the usual standard deviation. And you can calculate that as standard deviation of the difference equals the square root of 2 times the usual standard deviation squared, or 1.4 times the usual standard deviation. So significant change limits is the 95% confidence limits that define the inherent method variability. So if we're using those 95% confidence limits 5% of the time, right, or you'll be outside of those limits and the patient will be fine. But anyway, so you have significant change limits equals the mean value plus or minus 2 standard deviations of the difference, or the mean value plus 2.8 times the usual standard deviation, okay? So quality of control or process control and error detection. So that's the meat of this chapter is your quality control. And it's designed to detect errors in the measurement systems, okay? So there's 3 levels of the process. Each level's responsibility of a different individual's active communication amongst those individuals within each level is critical. The first level is us, right? Or not me, but you. the laboratory technicians, so, or technologists, and their supervisors too. You can always blame your supervisor, right? But they're the ones that are ultimately responsible, right? So basically, the responsibility, you have this daily analysis of quality control specimens, and then you're going to review and verification of patient results is another way. So daily QC, and then you look at the patient results and review and verify those reports, right? So we'll get into it in a little bit. Second level of QC activity ensures the minimal systematic bias enters into the system over a relatively short period of weeks or months. So that's going to be more of the responsibility of the lab director But the technologists do contribute greatly, right? Because they're the ones who are running all that QC equipment. And because they generate that data, the lab director can look at that over a broad period of time, and you can see if you get any drifts one way or the other, right? If it's slowly drifting low or high, you can look at the data from the QC data and determine that. Timely review of the QC data and proficiency testing results that have accumulated during that review period. So remember, proficiency test is like the CAP thing. Third level of QC activities ensures the analytical systems are as precise and accurate as possible. And that's going to be, again, the laboratory director or some sort of technical consultant that actually comes and verifies your machine, right? Reviews proficiency testing results. Knowledge of the levels of precision and accuracy achievable by other laboratories are going to be important. And you get that from proficiency testing, right? And using accuracy-based standards to verify or correct the errors. So, QC of the entire testing system requires additional process control measures, regulatory mandated monitors of individual steps in the testing processes. And your book mentions physician complaints. They shouldn't just be blown off. All those stupid doctors just always complaining, right? But they can typically be based on real deficiencies. Researching complaints may reveal faults that wouldn't have been realized otherwise, right? And ISO accreditation standards are important, right? What is ISO? Do you guys remember?
International standards.
Something like that. Yeah, where they come up with all the units of measurements and standardize across the globe of how to do measurements, right? So testing quality control specimens, making daily decisions. So daily prep and analysis of QC samples is regular responsibility of the analyst. And QC pools are analyzed as known controls during the analysis of patient samples. So what you'll have are these big stockpiles of quality control pools where they pool plasma or urine or some other kind of matrix together. And then you test that over and over and over again, and you come up with the mean value for that, plus a standard deviation of what you should normally see with that. So if you know the mean and the standard deviation for that, you can do these little charts that you're looking at, okay? So labs can estimate the target values of the control samples by repeated analysis, and that's what I was just mentioning. Or manufacturer's estimates can be used also. So manufacturer has to certify that there's this much, because you can buy quality control pools from vendors and they'll give you estimates, or you might want to use your own. A lot of facilities will come up with their own pools, just save specimens and pool them together and freeze them. Values can be determined by definitive or reference methods. And those are those, definitive methods is the best method possible. That'll give you a definitive value. And reference are just almost as good, right? Frequency of QC testing materials determined by each lab for each method. So really, it could be whatever, but there's some recommendations. Like CLIA 88 will require at least 2 controls for each one. But what is a run? So these days, I think typically they consider a run as like a 24-hour period because they're like constantly looking at samples. Or it might be a shift, like one crew shift is a run. So it'll change. The one thing that's different is I think blood gases are required, I think, more often. But anyways, quality control pools we were talking about. So most labs are going to use 2 different pools, right? You want to test values that are in a normal range and then maybe some abnormal range too. So you can see, make sure your accuracy and precision is good in both ranges, right? For your equipment. CLIA allows each laboratory to set its own protocols for chemistry testing of assay control samples as long as at least 2 control samples of different concentrations are assayed every 24 hours. So normal and abnormal would be 2 different concentrations. Special rules, however, apply for blood gas analysis. That's every 8 hours with calibrators instead of pools. right? Because you can't pool blood gases, right? Can you? No, I don't think so. So decision making. How do you make the decisions then? Testing personnel will use the data from each quality control analysis to make decisions about the validity of patient results. So you run the QC along with your patient results on the run, and you look at the values from that QC, and you determine can you accept that run or not. So if the results of the QC are within a target range, labs will set their own target range. We're going to go over some of these Westgard rules in a little bit, where they have these rules where you can standardize, but each lab has to come up with their own. So if the QC results are within the target range, you can assume the patient results are going to be valid also and accept the run. If the QC results are unacceptable, the run's not accepted, right? So decisions about runs must be documented in a worksheet, separate logbook, a data sheet, or in the laboratory information system, and include the decision, the analyst's name, and the date. So you guys know what's the LIS, the laboratory information system? So when you go to a lab, you'll see this more than you see these manual stuff like this, like what we're going to talk about is like the old school method of doing stuff. The laboratory information system's all computerized. So a lot of what we're doing today, the computer does for you, and it'll just tell you when you violated these rules. It tells you how to do, but we got to know where that comes from, right? What?
You violated them.
You'll see these rules. But first we're going to talk about how to choose a quality control pool, right? So the first thing we want to do is QC materials should have a matrix that matches that of the specimens that are tested on that run. And what do we mean by when we say matrix? A place to what? So the matrix is what the material's made of. Such as if you're running a bunch of cerebral spinal fluid samples, the quality control pool has to be CSF. If you're running urinalysis samples, the quality control material has to be urine and serum, etc. So it has to be matching, right? Because there might be some kind of interference in the matrix of your test samples that maybe if you're using a different matrix that the machine gets interfered with by the matrix of your test samples, but not your quality control material. So you want to make sure the matrices are matching. Large amount of QC materials needed every year. Several sources are available. Like we already said, there's commercial sources. Commercial lyophilized pool material, commercial stabilized liquid pools, frozen pooled patient specimens also. What does lyophilized mean? Sort of. Frozen, what do you mean? What kind of frozen?
Like, like dry,
freeze dried. Really, really frozen. Yeah, so lyophilized is just freeze dried. So clarified, frozen, or liquid pools tend to have lower standard deviations. Okay? Whereas, why is that? Why would clarified, frozen, liquid pools have lower standard deviations than lyophilized pool material? What are you adding to this lyophilized pool material that you shouldn't get from the clarified, frozen, or liquid pools? Huh?
Add water to the lyophilized?
Yeah, you got to add water to the lyophilized, which is a step where you're pipetting. So you're going to get error in that pipetting step when you're resuspending these lyophilized pools. It's one place to add a little bit of variation. And you see that with the lyophilized are going to have a higher standard deviation than your clarified, frozen, or liquid pools. Because those you just thaw and run, right? Liquid pools may experience greater instability errors associated with shipping batches of a lot to a customer because they're stabilized liquid. The shipping might not be good. It might be 105 degrees in the back of a UPS truck with the dry ice all gone after it gets delayed and cause some degradation, right? So there might be some instability errors with liquid pools. Testing for virus should be done on pooled patient controls and not used if found to be positive, right? Because if you're using pooled patient samples, you don't want to have HIV or Hep C or hepatitis positive samples that your technicians are constantly working with over a year's period, right? So you got to test them, make sure they're free of virus because it's a bloodborne pathogen, right? Those pools you don't want to have, infect you guys. Controls require freezer or refrigerator space for up to a year to 2 years supply. So when you get this, you get these huge supplies, and then you're going to store them. You need a good place to store them. Considerations for estimating limits of QC pools. So unless the true values are determined via definitive or reference methods, target values are only averages of repeated measurements of the pool. So you're going to repeatedly measure these pools over and over and over again and use the average. CLIA 88 allows the pool's manufacturer to establish the target values with the laboratory confirming that each target value is applicable to its testing system. So if somebody has a testing system that has different bias than the manufacturer's, it might not be very applicable, right? So a new lot of QC material should be tested in parallel with the old lot. So before you shouldn't just run out of the old lot and then, oh, we got a new lot, because that's not going to be the same. You have to verify that new lot and the values for that new lot before you can get rid of that old lot. So there's 3 methods can be used to establish the limits of acceptable values for a control pool. You're going to use medically allowable error for choosing the range, estimate the target value and the usual standard deviation, or employ the use of power curves. So what you want to do is basically get a year's supply of the QC test material to start off with. And you want a 6-week lead time, and compare the analysis of old and new lots that you run together. So you're going to run the old lots and the new lots together. You can do data reduction, calculation, and evaluation of the control limits. Always follow the directions while reconstituting lyophilized materials. So that is variable. Lyophilizing the reconstituting lyophilized materials will add variability. Test duplicate samples from 2 different vials each day for 10 days. And then you're going to determine the temporary target values for the constituent, for each constituent via the mean of those 40 values. So if you're testing 2 different values each day for 10 values, 10 days, that will be 40 values, and you'll be able to have a temporary target value. You can calculate the standard deviation of those 40 values, and after the 3rd month, use 4 values to calculate the final target, the temporary target value, and the 3 monthly averages. So every method has its inherent variability, and we can define as the usual standard deviation. The usual standard deviation is calculated from a series of 3 to 6 monthly standard deviations and obtained when testing when the instrument is stable. If the instrument's not stable, that'll throw off your usual standard deviation. So the instrument has to be running properly, and then you'll develop this usual standard deviation. And then you can use this usual standard deviation as a valid estimate of the day-to-day variability. So with your new pool, you can use this as your estimate of the standard deviation. And it can be used instead of that temporary standard deviation. So action control limits. CLIA specifically defines the term out of control as a situation in which a testing system cannot be used for reporting patient results. Often results in shutting down the procedure and then troubleshooting why are these results bad. So exceeding action limits is the term used when QC analysis exceeds the set limits. It does not involve shutting the procedure down. So a lot of times they'll use 2, 2.5, or 3 standard deviations as the action limits, right? So if you're using 2 standard deviations as your setting, as your action limits, and you exceed that, how often should you exceed that if everything's fine? 5% of the time. So if you're shutting down your procedure 5% of the time, for no reason whatsoever, just because you exceeded the action limits, then there's something wrong with that, right? So you could go to 3 standard deviations instead of using 2, plus or minus 3. How often would you exceed the action limits then? So it's about 1% of the time, a little bit less than 1% of the time, right? So, but then you might not be able to detect error as well, right? Because you might shut down the procedure, you might exceed the action limits less, but you might not have as good error detection. So, historically, action limits are set plus or minus 2, covers the 95% of expected control values. 5% of the results are accepted, I just did all of this, may result in false rejection runs. Some labs will use 2.5 or 3, but when you go this high, it may not result in sufficient error detection for medical or CLIA requirements. So out of control decisions. So out of control exists when the validity of the results are not considered to be appropriate. Determination is made by the director or technical supervisor. Minimum out of control criteria, control values exceed predetermined out of control limits within a specified period. A method is determined to have inappropriate reference intervals. A method demonstrates unacceptable imprecision, nonlinearity, or interferences. A pattern of inappropriate patient results with large numbers of abnormal values is observed. Because that's one of the things with the QC also, you got to look at your average patient results. They should follow a normal distribution with some, like not 5% of the time generally, outside that normal range. And if you see all of a sudden you're getting way more abnormal ones than you normally should, then that's something to look at too. And then the laboratory director can just declare it out of control for whatever reason he wants to. Right? So basically we got 4 different outcomes of a run, right? Can anybody tell me those? I know you can, right? So we got good data and we got bad data, right? So good data that's in is a true accept, and that's what we're looking for. Good data that's out is a false reject. And you're going to have, you should get, if you're using 2 standard deviations, you should have 5% of the time a false reject. And then you got bad data, and that tells you when you have bad data, there's something wrong with your machine, and it could result in a false accept or a true reject, right? So the 4 outcomes of a run. So how are you going to detect these quality problems? Like I told you, these days, the computer will tell you all these Westgard rules and tell you, they'll probably program it in there how to do this. But control results can be reviewed in a variety of ways. Compare results with a posted range limits the ability to employ other analysis, and we're going to talk about Westgard rules. Computer assistants can allow real-time review of control results, allowing for early detection of QC problems. And Westgard rules are based on these Levi-Jennings plots. These were the plots you were looking at. And basically, it's daily analysis of QC results are plotted to create a graph. You have the mean in the center, and then above and below, you have standard deviations away from the mean. And then on the horizontal axis, it's the run, or the day. So expected analyte concentrations, established target values, the desired number of SDs are drawn on the y-axis, and the days of the month on the x-axis. And you get these types of graphs, right? So stable performance should show you distribution around the control limits like that, right? Where you're going to have normal, some normal outside of the range. This represents a shift in the mean, right? And this is what the graph is going to look like. You plot the controlled data, and normal data is going to have a distribution like that. It looks similar to this as you go through the days. If you have a shift, like this is an example, it shifts down one way, so there's something wrong with your accuracy all of a sudden, right? Or if you have an increase in variability, also is going to result. It's going to shift your population of control data, make it more broad, and you'll exceed the control values more often than you should. And I think this is the one from your book. I think I like this one better, but what do you think? Huh? For understanding the graph? You like this one better?
Would you recommend the test?
So on the test, there will be individual graphs, and you got to tell what the points are. And then we'll go through some more examples. So 1974, the College of American Pathologists, they came up with these Westgard rules. And it basically has to do with the daily decisions for like a two-pool program, except the run if both runs are within 2 standard deviations of the established mean, right? Because 95% of the time, one will be within that, and most of the time, both will be within 2 standard deviations. So if they're both within 2 standard deviations of the mean, there's nothing wrong. You can assume the patient's results are fine too. If you have one control within 2 and the other control less than 3, you're also going to accept the run. Okay? You reject the run, however, if one control is greater than 3 standard deviations away from the mean, or both controls are greater than 2 standard deviations of the run. And then they get these these are the rules. So if you have a 1-3S, that means that one of your control samples is greater than 3 standard deviations away from the mean. So that's the Westgard rule that we break when this happens, okay? So I think your book does a terrible job at describing these rules. So I didn't understand it the first time I taught this. So I kind of glossed over it, but now I understand it a lot better. So both controls, so you have a 2-2S. There's 2 different types of 2-2S's you can have. This is in one run, both of the controls are exceed 2 standard deviations, that's a 2-2S. Or like here, if you have one that exceeds 2 but less than 3, that's still good, but the very next run, you have another one that's above 2, then that's another 2-2S rule violation. So 2 standard deviations 2 samples that exceed 2 standard deviations away from the mean, it's a 2-2S rule violation and a 2-2S rule violation. So we'll go through some of these. These were the rules, and they were published by Westgard back in '81, a long time ago. And it has to do with, not rejecting runs when you just have normal variation. It's also a way to troubleshoot. So computer-assisted evaluation of the run data, you have 2 controls per run. If you look at the data, is one value greater than 2 standard deviations? If that's yes, you look again. Computer starts here if it's one's at 1.3 SD. If that's true, then you freak out and you stop and troubleshoot what happened. Why do you have one value that's more than 3 standard deviations away from the mean? Which could happen, less than 1% of the time. So it might not be anything. And this is what the data looks like, right? So this is O's and X's are your different samples. You could have a high quality control pool and a low quality control pool. And they just graph it like this versus the mean and then the standard deviations. And then these are your days or your runs. So with this one, it's less than 2, or it's right at 2 basically, and this is less than 2, no problem, no problem, no problem, no problem, no problem, no problem. And then up there, 1 is above 3 standard deviations, so that one is you're going to stop and troubleshoot. So how do you troubleshoot? This could occur, if it's random, due to the control material, a short sample, or a mix-up in the control. So those can result in it being like that. If it's systematic, it could be an issue with the reagent, or the calibration could be off, right? And thus it's difficult to troubleshoot without more information. So to get more information, you're going to go to the documentation. And then here we find out that recalibrated the lot with 123.mm, it expires 8/10, and that's signed, so it could be the calibration then. So evaluating 2 controls per run again, look at the data. Is one value greater than 2 SD? Yes. then 13SD, it's in. So the two values are two SDs. If you have two standard deviation, that's the rule, 2S, or did I say that right? I don't know. Then if you have two that are greater than 2 standard deviations, then you freak out and stop and troubleshoot. And this is what that looks like, or one of the examples of a 2S, right? So normal, 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 and then boom, all of a sudden, both control samples are greater than 2 standard deviations. Yes?
Question. So basically, like in anything within this 3 standard deviations, then you have to consider it as an error?
Anything within?
Yeah.
Anything greater than 3 standard deviations is going to be a 13S error that you have to stop. It's a rule violation, 13S. This is an example of a 2S where you have 2 samples that are greater than 2 standard deviations from the mean. So, which are these? And these are both on one side. So what could that be indicative of? That could be like a shift all of a sudden, which could be bad calibration or something along those lines. All right? So across the run, 2S equals what? Systematic error? So this is another example of 2S, right? So this is in, these are in, these are in, these are in, these are in. Oh, this one has 1 greater than 2 but less than 3, right? We still accept that run, but then we do the next run and look what happens. It's, yeah, so we have 2 standard deviations, or 2 samples that are 2 standard deviations, and these are consecutive runs. So that's a 2S violation again. So like I said, run 6 is accepted. There's no rule failure when you just have 1 that's greater than 2. If you have 2 that are greater than 2, then that's an issue. So this is another rule. It's R4S. So look at the data. 1 value greater than 2, yes. Is 1 greater than 3? It's in, so that's fine. 2S is in. R4SD. What does that mean, R4S? What this means, it's an increase in your random error. If you have both are 2, this is, a lot of people, when I put an example like this on the test and you got to name which Westgard rule it violates, they'll put 2S because you have 2 samples in 1 run that are greater than 2 standard deviations away from the mean. But what this rule violation really is an R4S because they're 4 standard deviations apart.
They're on opposite sides of the equation.
Yeah, which tells you that there's greatly increased imprecision. See, I always get those words confused too. Greatly increased imprecision in the machine. And that could be have to do most likely something that you did, like pumps, tubing, electronics, or control mix-up. So it's going to be random, something that's going to increase your random variability. So another one, 2 controls per run. If there's no computer, look at the data. Is 1 value greater than 2SD? Yes. This sums it all. So if you have 1, you got to stop. 2S you stop, or R4SD you stop. So, otherwise, you just report the data. So probabilities of a false reject when you have an N of 2. So 0.67% with a 13S. So 0.67% of the time you're going to have normal data where you exceed 3 standard deviations of the mean. 0.25% of the time you should get 2 successive, you're going to have the 2S violation, and 0.25% of the time you'll have an R4SD. So that totals to about 1.2% of the time. Everything's going to be fine with your machine, but you're going to reject it. So they use these rules rather than just the 2 standard deviation rules because you have good detection with fewer false rejects, right? Which saves the lab money and gets the results reported faster. So you don't have to rerun patient samples when there's nothing wrong with your machine. So that's why they came up with these rules. Does that make sense?
Muddy water.
Huh?
Muddy water.
So, but you can even reduce that even further if you have 3 controls per run, and they have these. So again, you have 1 3SD, you're going to fail. If you have 2 of the 3, you stop and troubleshoot again, or a 4SD, you stop and troubleshoot. So 3 controls looks like this, right? And this time we have O's, X's, and pound signs. So all of these are in until we have what these, this would be a 2-2S, right? Using 3 controls. And an R4S again. Do you get these pictures now, Shafina?
I get them, but I'm practicing to see if I actually really get them.
Okay. So again, this is like an R4S because you're greater than 4 standard deviations between those 2 controls. And then if you're including 3, you have a 1.8% chance of a false reject rather than, what was it, 1.2 before? But you might be more likely to detect when there is a problem. So fewer false rejects, better turnaround time, lower costs, and less frustration is what they say for that. So using the patient's data in decision making, most patients' results fall within the reference intervals established for each analyst. I think I touched on this a little earlier. And it's normal to have results within a healthy range with a few out of an abnormal range, but if all of a sudden we get a bunch of abnormal results, that should have you look at your equipment because it's, or contact the CDC because you got some outbreak of something, right? But so distribution of abnormal results will vary from test to test, but deviations from the usual patterns that the hospital normally sees of cumulative patient results should alert testing personnel that there might be a shift in the performance occurring. Because if you have all of a sudden half the people are abnormal one direction, then it could be a shift in the accuracy, or if all of a sudden it's both ends, it's an increase in precision. What's a delta check? Do you guys know what delta checks are? So it's a quality control check, but it uses patient sample, and it's a pattern of consecutive results of an individual patient. So it's almost like looking at that, you know, that daily test, and if it changes excessively, you shouldn't see a large difference unless there's a major medical change has occurred. But unexpected changes from a single patient's serial specimens are called delta changes. Delta limits are made to detect misidentified specimens or other errors. So sometimes if the specimen's misidentified, it'll cause a delta limit to be exceeded, and that just because, why do you have misidentified patient specimens?
Forget to label the tube a little bit before you leave the room.
Exactly.
Although that still says individual specimen.
Could be. Analysts must determine whether the change is real or caused by some other problem or not identified by QC. Specimen indices and flags. So these automated machines we have in the clinical lab, they'll just flag a sample when there's something wrong with it right off the get-go. And the most common interferences are hemolysis, lipemia, and icteria. So hemolysis is going to cause a lot of heme in the sample, and that's going to absorb light, right? Lipemia, you have chylomicrons or VLDLs contaminated in the sample, and that's going to cause light to scatter, which is going to throw measurements off. And icteria has high levels of bilirubin. You guys know what icteria is? Or you get high levels of bilirubin in a plasma sample, it absorbs light also. Why would you have high levels of bilirubin?
Jaundice.
Yeah, jaundice. Alcoholic hepatitis or something. So automated instruments, they'll quantitate the degree of such potential interfering factors, and if it's too high, they'll flag that specimen and you got to dilute it. So newer instruments will flag the patient results indicating significant problems with the result, and technologists are alerted in real time when problems arise along with corrective action. Adequacy of the specimen for the test being performed, specimen-specific problems with the analytical system, or verification and release of individual patient results. So if something wrong with like if it's a lipidic sample, a lot of times you got to dilute that down to where the scatter will be insignificant. Same thing with hemolysis or icteria. So this is an example of your daily quality control runs, and these are, again, this is from your book, and these are basically your Levi Jennings charts, right? So for all the different values, these look good, and then these are outside the range. So I don't like the figures in this book so much. More like the animations I like. But apparently, back before computers in a clinical lab, they used to post these, they would just tack them up to the wall to do it every day, and then you could have a visual representation of where all the runs are, so you can clearly see when you're getting a gradual, not a shift, but what's it called? Trending one direction or another, and you're getting some skewing. So, but these all look okay except for those out of control actions. Use of calibrators. So your control pools cannot be used to calibrate your instruments, right? Each has a separate and important function, controls and calibrators. Calibrators are set to set the reported value's accuracy. So you calibrate your machine with something that's known, that's been measured and certified and traceable back to the method that determined its concentration or weight. We'll see, so we have calibrated weights for this thrilling lab we're going to do. So, but the controls just verify the stability and accuracy of the calibration in the testing system. So you cannot calibrate with controls, but you can use calibrators as controls if you have to, right? But never use your controls as calibrators. So CLIA 88 allows for calibrators to use as controls for tests in which suitable controls are not available, but never use your controls as calibrators. So commercially available calibrator has an assigned value that the manufacturer established using definitive or reference methods or by using reference materials traceable to some primary standard. So calibrators are used to set the value reported by the laboratory's method or the instrument. So basically it corresponds the concentration in the calibrator to the signal, the electrical signal that the machine detects based on, analyzing that calibrator. So you set it to that voltage or signal, the absorbance, whatever, and then it'll calibrate it in the machine. So in patient samples have the same voltage, it's going to have the same, pop out with that concentration or weight or whatever. Calibrators are usually purchased in lots, enough for 12 months or longer again. Quality control of reagent changes and instrument maintenance. So each lot of reagent or separate shipment of the same lot must be evaluated for quality before it's put to use. So you have to test it, right? Because that's a lot of times you'll see the QC material go out of whack when you change lots. So laboratories can show that the new lots are acceptable for use if after their use of control values do not change significantly, and after maintenance is done, test several controls and patient samples from a previous batch before resuming the testing. So chronological records of all reagent changes, instrument repairs, and maintenance procedures, along with any calibration verification tests performed, must be kept. So that goes when you violate those Westgard rules, you can look at the maintenance record and say, oh, we just calibrated it, that's why we see a shift and have this 3SD result, right? Or 1,3S result. So then you have to recalibrate it and test it again to make sure the run's okay. External quality control programs and other tools. So accuracy control is required by CLIA 88. and that includes proficiency testing samples. So they're used to evaluate the adequacy of laboratory performance in all laboratory specialties. Failure of a proficiency test has severe penalties. Proficiency testing provides independent validation of your internal quality control. So basically, they give you test samples, you test them, and you send them back the values you came with those and your standard deviations for those. And they compare you to everybody else they tested. And if you're so many standard deviations away from the group mean, then they fail you. And then you could lose accreditation in the lab if that occurs. Proficiency testing can provide an estimate for the inherent accuracy of the system because it basically compares you to everybody else. And estimation of the system's bias can be made from proficiency testing performance also. So definitive and reference methods. Established by the National Reference System for Clinical Laboratory. Definitive method, if you guys remember, is the most accurate way that a particular chemical substance can be made. So if there's definitive methods, a lot of times it's like HPLC, MS, things like that. Real expensive, complicated methods that you can't do on a regular basis. A reference method is less rigorously proved than a definitive method, but it's well accepted because there is considerable evidence of its analytical abilities and demonstrated a record of transferability of accuracy. Field methods are the ones that are in common use, and that's what we're normally going to use. So reference materials have the true target concentrations of calibrators are assigned by the use of definitive and reference methods and can be certified as certified reference materials. So a lot of times your calibrators are going to be reference materials. So they're certified. Alternatively, reference materials can be produced with known quantities of high quality analyte, right? So if you just have the analyte super pure, you know how much there is, you can add a certain volume of matrix and it should be that same amount, right? Other materials are available that have consensus values established by thousands of laboratories. CAP produces survey-validated sera. And primary standards are always required for definitive and reference methods. So NIST will provide a number of standard reference materials that may be used to prepare primary liquid standards. And matrix of the prepared calibrator needs to be consistent with your test, remember? So if you're going to be testing urine, you calibrate the machine using a urine matrix. Okay? And then that's it for this one. And we got to go do the lab, I guess.